Dun, dun. Hi everyone. Well, welcome to my talk. It's about the now and the future. I'm not sure if I even need this. It's about the now and the future of malicious WebAssembly. And well, I'm a PhD student from the Technical University of Brunswick, and this is work together with my colleagues Christian Wessnecker, Martin Johns, and Konrad Wick. And this is about our study on the WebAssembly ecosystem in general, and then I will more focus then on the current and future potential abuses of this technology. But keep in mind, I'm a PhD student, so this might be more of an academic work. So one of the things the web has always struggled with is, well, native performance. So if you think about something like games in particular, or anything that involves 3D, there were some attempts, like Adobe's Flash was popular for a while, especially for games. And then we also had the ActiveX, and Google's native client. But they are all, well, by now they're either deprecated or scheduled to end soon. So this is not really the future, this is the past, right? What we also had was ASM.js, if you ever heard of that. It's basically a subset of JavaScript. They did some clever optimizations so that they could speed up the process if you only use some parts of JavaScript and not others. But that led to faster execution, but it still was only like a band-aid afterwards. Like, so we already had this JavaScript, so how could you would make it faster, but it's not like that they didn't recreate it from scratch, right? So that's what they actually did with WebAssembly. They introduced a whole new language basically to the browser. So it's been there for over 2 years now. As you can see, it's quite well supported. I mean, if you can read it, but the important browsers are all supported, or those that are widely used. So, and the cool thing is also running on iOS and on Android. So you not only have desktop applications or desktop computers, but also all the mobile clients. So this is cool, but well, what is it actually? So it's low-level bytecode language, and what it makes as an effect is it makes everything faster, right? So we have faster transmission because the size is just smaller. If you have the code equivalent code in JavaScript or in WebAssembly, it will be just smaller because it's binary format. And it also the compilation is much faster and everything because they designed the format in a way that it just, well, is better to optimize compared to JavaScript where you have expensive parsing involved. So here, just as like a rough estimate, there's a very good series by Lynn Clark, which is published on like the Mozilla blog. And I've just taken 2 images from there. So this is the typical amount of time it takes to like execute the JavaScript code. So with all the steps involved. And obviously it's not like a total amount of time. It's just like in relative for like an arbitrary piece of code. And this is how it would look like with WebAssembly. So as you can see, many steps are much faster, and other steps are just plainly not there anymore because they are not needed. So we can get a lot of more performance in the end. So our sites load faster, and the things that they do inside goes also faster, which is great. So just to clear up some confusions, you wouldn't write WebAssembly from scratch. So it's like the output of something that you already do. You write code in C++, and then you say, okay, now export it to the web. So what you would, for example, do is have this cool game here, which is, it might be a little bit out, but this is Diablo 1. And somebody ported it, so as you might be able to see, this is running in my browser. So we have the URL bar at the top. And what I also want to try, because I don't think I need the full time of this lot, I also want to show you something else. Because you might say, okay, Diablo, well, it's maybe 20 years old or something. It's almost as old as I am, this game. So what about something newer? And I found this one. And let's see if it works. So now we have Doom 3 running in your browser. Let's skip the intros. Okay, the resolution is a bit problematic because I can't access the menu. Let's see. I see it. Yeah. Oh yeah, there it is. So we can now play Doom in our browser. And they didn't do much work. Like, you might maybe change things around a little bit. So if you depend on something that's only available in Windows, on DSL or anything, then it might be problematic. But mostly you can take the existing code, and that didn't work that well. Let's give it another try. Alright, so here we are at the beginning of the game. You can see it's a 3D game. It's like 10 years old, and the resolution is, well, very limited because of but it's only due to the beamer. So yeah, the rest of the presentation will be me speedrunning the game. Have fun. Also, did you know that you don't have to stand on the scanner? Oh. Wait a second. Come on. So he doesn't scan you.
You're gonna need to hold still. Moving around only makes the test take longer. Alright, bioscan looks good.
So the bioscan looks good, but I didn't stand in there. Anyways, okay, that was the demo. Let's get back to the presentation. So this is especially cool for kids who are in school with their Chromebooks and they can't install stuff. So if they're bored at school, they can now play Doom 3 or maybe something less violent, I hope. Okay, so let's get back to the technical stuff. How would you... So I don't want to go into the WebAssembly modules and the structure and everything. I only want to show you how you would use it from JavaScript. So in this case... here, we assume you already have your WASM file on the server, so WASM is just the extension for WebAssembly, and you already have it on the server, and you now want to like run the thing in the browser. So what you would do is call this instantiate streaming, which is also cool because like it's an asynchronous function, and while the download for that WASM file is running, because you can imagine for a game it might be large, like 20 megabytes or even more. While the download is running, you can also already partially compile it. So this instantiate streaming is like doing this thing on the side because they created the format for WebAssembly in a way that you can already start with the compilation, even if you only have like half of the file or something. So that's one of the reasons why it's faster. And then you can also see I have this object at the end. Try if I have my laser pointer here. Yeah, we have a laser pointer. Okay, so you might wonder what's this object about? Well, these are the functions that I want to import into the WebAssembly. So what you need to know is that, like in JavaScript, you have access to all the things like the window and the DOM and the console and everything. But in WebAssembly you don't. So it's very, very like isolated from the rest of the browser and the rest of the world that you've known about. So here, if I want to actually from the WebAssembly code want to write something to the console, then I must make the console available to the WebAssembly space. So here I just have imported the function here at the top, and then redirectly like change the arguments through. So okay, so now we could call back from the WebAssembly world into the JavaScript. But what we also need is the other way around, right? So here's an example. Basically, all the functions that you export in the, like imagine Z where you have imports and exports. All the things that we export, we can now call from JavaScript. So it's important for you to realize that it's not like, oh, forget all about the JavaScript, now we're writing our websites in WebAssembly. Like that won't happen. These two things complement each other. So you might have an algorithm that is very CPU intensive or that you want to speed up because it's called very, very often in your software. And then you can basically write that in C++ or whatever and call it from a JavaScript and then use the result as I'm using the result here, back in the JavaScript world. So these two things can call into each other, right? So that's important also for later. Okay, so far for the basics. Another thing I want to clear up, because when I discussed this with folks, it led to confusion in the past, so let me clear it up before there are questions. So one thing you might say when you hear about this new technology is like, oh no, now I have to wonder about buffer overflows being in my page. Like, oh my god, and then you already have XSS and CSRF and all this stuff. So now I have to worry about this too. Or you might say, whatever, this talk doesn't really affect me because my website just doesn't use WebAssembly, which will probably be true for most of your websites at the moment because it's not used very widely. Yeah, it's kind of true, but also the problem is, so far from what I've seen, to trigger something like a buffer overflow in a WebAssembly module would also very likely already require code execution. So it's not like they're exposed to the outside. I mean, you could imagine a theoretical case where a WebAssembly module takes something directly from the URL or something. But anyways, usually you probably already have an XSS in your page to be able to trigger the buffer overflow or whatever in the WebAssembly. So I would say at this point you have other problems than that, right? Also, they have some protections in case, namely they have some control flow integrity and protected call stacks and whatever. So I think it's much harder to execute than in most other platforms. So that means I'm not talking about cross-origin attacks where I'm attacking your website because it uses WebAssembly. No, that's not the point, actually. So what I'm talking about is attacking you with an arbitrary module. Because you have to remember your browser most likely supports it by now. Unless you're using Internet Explorer 11 or something, but again, then you have other problems. So if I can lure you onto my website, which might be easy or might be hard, but I send you a link or whatever, then I can execute any WebAssembly module that I want, right? And that will make some attacks more stealthier or more worthwhile, as I will basically show now in the rest of my talk. Okay, so yeah, as an academic, I just wondered, like, how is the landscape looking? What is the ecosystem looks like? So we have to investigate that first. So just a few details, maybe it's of interest to some of you here. Basically, the data collection is just we crawled lots of websites. So we used the Alexa Top 1 Million, which is like a popular list of websites. And we also crawled some subpages there. So it's, if you only visit the front page, imagine there are websites that have lots of games, but on the front page, they usually just show you a selection of all the games. And only if you click on one of them, then it actually like loads the game. So if you only visit the front pages, then you miss lots of stuff. Anyways, and it's not so easy to collect those WebAssembly modules. Like if you want to, if you're like me and just want to collect all the WebAssembly modules to look into what people are actually using it for, then there are multiple options. So the first one that you might stumble upon, which is referenced on the web sometimes, is like use this dump wasm module flag. So it's like a V8 flag for Chrome, and then all the WebAssembly modules magically appear on your disk. The problem is it just didn't work for me, and after a while I figured out that it only works if you have a debug build of Chrome, which is a bit unfortunate because that thing is huge and takes a lot of time to compile. And then maybe you work on multiple platforms, like I have this Mac, but then the crawling is running on a Linux machine, so suddenly I need two builds because I want to test it here and then run it there. And then that sounded like too much hassle for me, to have all these builds constantly updating. So the other thing is you could use this debugger script pass, which you mainly use to intercept all the JavaScript parsing, but you can also use it to intercept the WebAssembly, but it also has some drawbacks. So basically, in the end, I just wrote my own wrapper around all the JavaScript functions, like the initiate streaming that we've seen before, and then locks it to some backend. And I've just included that here because after we published that, I got multiple questions about like how can you also like do something like that. And then in the end, I just decided like I put this on GitHub, the small like this wrapper script with some Puppeteer that just visits the website and runs the script. Anyway, so if you ever want to do something like that, here's the link. Okay. So what did we find? Well, not so much. So remember we visited 1 million sites, and about 3.5 million pages, and we found around 2,000 WebAssembly modules. Okay, but then of these, only about 150 were actually distinct, so like where at least one byte differed. Oh no. It didn't do anything. And some of these modules were quite popular. So there was one module which actually was on 350 pages, as you can see here. And then other modules were just like unique, like you never saw them again. So these 87 modules just seemed like a one-off thing that's not reusable. And yeah, because like I said, PhD student, we need lots and lots of graphs and stuff. So I just included them here. Here we can see that the more popular pages were on the very left here. The 100,000 most popular ones, and these are the least popular ones. So we see there's like a slight trend to that the more popular pages also use more WebAssembly or just try it out first or whatever. But it's not like, so it's distributed around web. So people are using it also on less popular sites, is what I'm trying to say here. Then how much are they using it? So the question is, I mean, you could have a WebAssembly module in your page, but is it like an important part of the page, or is it just like a random thing that you actually don't really need? That's kind of hard to investigate without looking at each individual site manually. But I just did some quick measurements. So we had the smallest module was only 8 bytes, so that might also already give you a guess about how important that might be. And then others were like in the range of about 20 megabytes or more. And just comparing that, we can see that the JavaScript code is still much larger. I know that's biased because JavaScript is like a textual representation, and as I told you, WebAssembly is binary, so we expect WebAssembly to be smaller, but still it's like order of magnitude smaller. So I would say most of the web is still written in JavaScript. Surprise. Also, we wanted to find out how much CPU is using WebAssembly compared to JavaScript. So on this graph, it's relative. So the bar on the very left means this website used basically 0% of the time was spent in WebAssembly computation. So it's basically just using JavaScript all the time. And on the other hand, on the very right-hand side, we have websites that use up to 100% of the CPU time spent exclusively in WebAssembly code. So they don't execute JavaScript anymore, or very little of it. And you have to keep in mind this was without user interaction. So we had some crawler that was unsupervised and just left visiting websites, and you did not click anywhere or something. So most of the games where you also expect a heavy CPU usage, well, they were maybe stuck at the menu, but nobody did play it, right? Okay. One more graph. Oh yeah, people don't like my graphs, I see. One more graph, and then we're back to more, let's say, down-to-earth applications of WebAssembly, where you will see what they're actually doing with it. But basically, this thing is a bit complicated, but this huge white thing here is one cluster where we had lots of files which were basically all the same. And this thing here is one cluster, and then this thing here. So yeah, as you can see, we had in the beginning having 2,000 modules, then we checked if they're unique, and it was only 150, and then we also clustered them with some magic, and then it turns out there are only about 11 clusters of really distinct stuff. So it's not that much out there. But so far it didn't really help us, right? So we're not that much wiser. We just have looked at this in an aggregated fashion, and we see like, oh, there's the clusters and stuff. But like, what are people actually doing here? So all the statistics and stuff didn't help. I actually had to manually analyze all the 150 modules and the websites that were using that. And I labeled them into different categories. So let's start with the less interesting ones. There were some that I would just call unique, where people just randomly tried experiments with WebAssembly. So there was this neat background animation written in WebAssembly and stuff, but nothing really of value there. Then I found out that there were quite a lot of libraries, or let's say there were a few libraries which were used then on many sites. So for example, the Draco library is about decoding 3D models, and you might not even be aware that you're using that, right? So you include some library from GitHub on your page, and then under the hood it uses WebAssembly, but it's not like there was some developer that said, oh, I want to try this cool WebAssembly now, and I will include it. No, it's just some third-party dependency. So also not that interesting. There were also some I would just call tests, where people like try to test if WebAssembly is available. So you could do something like check if the WebAssembly API is available in JavaScript, but people don't seem to trust it really. And so here is the smallest possible WebAssembly module that you could create that is still valid, so that doesn't crash. And we had lots of sites, like 250 of these, which execute or try to instantiate this module and see if there were any errors. And if there aren't, then they do something else. So you can use it just as a test if WebAssembly is really, really supported. More interestingly, there were lots of games out there. So if I can recommend you two, that's Take Point on the left and Slither.io on the right. These are quite fun, but there are also more out there. So people are obviously using, like I showed you in the beginning. This is one of the examples that we actually want to see, right? So that's good stuff. But unfortunately, we also had some other stuff found, right? But for that, I have to do another digression because I'm not really sure how familiar you all are in the topic of cryptocurrencies. So just one slide about mining. Mining is the process of minting new coins. So imagine something like Bitcoin. And it works in a way that you take the current state of the network, whatever that is, and you add a random number to it that you just choose to your liking. You calculate the hash of all this stuff and basically compare it to a given target. So you check if it's a very, very small number, that hash. And so if you're choosing a random number that luckily leads into a hash that has lots and lots of leading zeros, then you would basically have mined a block. Maybe you heard of that term before. So it's just lots and lots of computation. Why would you do that? Well, if you're able to do this process correctly and get this very low number, then you would get new coins basically for free as a result. And why you shouldn't do that, or what's the problem? Why is not everybody doing that? It's because there are some cost involved, obviously. So you need the hardware, and more importantly, you also need the electricity. So you pay for the electricity usually. And like you wouldn't have one computer, but you would have this giant farm of ASICs and stuff. So you would, your profits are severely limited by the amount of computation that you pay for. So then some clever people came up with the idea, well, maybe somebody else can pay for the electricity, right? So if I have people visiting my website, and they run this miner in their browser for me, that's what the crypto checking was all about, then I don't have, so then they are paying the electricity for me, right? So this is the crypto checking, and surprisingly or unsurprisingly, whatever, we found that the most popular usage of WebAssembly was implementing a Monero miner for the browser. So then people would visit your website, and then they would run this WebAssembly miner in the background, and basically all the computation would not be for the benefit of the user, but rather somebody that included it on his website. And also you have to keep in mind, so we found it on around 900 websites, but we did our measurement around here. So this is Monero versus the US dollar. So as you can see, there were some points in time where Monero was really worth a lot more than it is now. So there were reports like around here from way more websites, like over 2,000 or something, near like the 1 million. So this is already like the big chunk already passed, but we can still see it on a lot of websites. And also, if you ever heard of CoinHive, which was like the largest provider of these mining services, they shut down this year, so the numbers are probably dropped by now further. But who knows what happens in this cryptocurrency market, or if Monero ever will be of more value again. So, yeah, we found these miners, and they also explain, like the graph that I showed in the beginning, remember, with the CPU. This is basically the same graph, just with another notation on the axis. So this is the logarithmic axis, just to screw with you. No, so that you can see these smaller numbers better. So basically, what we had before with the WebAssembly that was using 100% of the CPU, that was the miners. What is basically what the slide is saying. So the gray stuff is the miners, and the white stuff is others. Like all the other categories, like lighting, we see. And if you have no user interaction, then it's the miners that really use the CPU. Okay, so far so good. We also had some other cases. So people were also using WebAssembly to obfuscate their code. And we only found a few samples of those. So here we had, basically so the script here is normal plain JavaScript. But what you need to know is that it was hidden in the WebAssembly module. So you have this, in the WebAssembly module, you have this memory section where all the strings are contained. And they use these memory sections to like slice the script up and hide it in multiple WebAssembly modules. So you might have one module for the first line with like this one where the pop under is initiated, and then you have one WebAssembly module where the URL was hidden, and then another one that closed the script. And so you had to combine all these modules in the right order, and then only then you would get the script that actually is later inserted into the DOM. So it's not that super hidden, because still at some point you have to add it to the DOM and then it's observable. But it's harder, like if you imagine something like an ad blocker or some malware detection engine, whatever. It's a bit harder to like see what's happening there, because it's the scripts are not like transmitted over the network as JavaScript, but actually hidden in the WebAssembly. And we also had one module that implemented an XOR cipher and nothing else. So there was just this module sitting around that could be used for encrypting and decrypting stuff, but it was not used. So that was a bit suspicious. But who knows what they planned for. Okay, so this is basically a huge summary. And as you can see, unfortunately, the cases that I would label as malicious, that's the mining and the obfuscation, together, because thanks to the large amount of mining, make up for more than half the WebAssembly usage in the wild currently. So, yeah. Thanks, attackers, for adopting this technology very early. Yeah, so I just have a few notes about the future. I mean, the talk was about the now and the future, but as you can imagine, I don't have a crystal ball, so the talk obviously mostly focused on the present. But I still try to like draw a little bit picture of how or where this could be moving if people are really in a malicious mindset, I would say. So what we've already seen is the embedded HTML JavaScript something. So you just use WebAssembly to hide stuff very, very simple, in a simple fashion, right? But then we could also imagine like you could do something like unpacker or decryption routine in WebAssembly, just a very small thing. And it would basically hinder all the static analysis of JavaScript if you are unable to determine where the decryption is, how the decryption is running. So imagine you have a system that is used to analyze JavaScript, like you need a little sandbox or something, and it's unaware of that WebAssembly is a thing now since 2 years. So that could really hinder at least static analysis if there's some part of the code that needs to run WebAssembly, right? And what's more, well, you could just in the future write your exploits basically in C++, browser exploits, and then export them to WebAssembly. So you could imagine an attack where there's just no JavaScript running on the page, and the full exploit chain is running in WebAssembly. So yeah, that would make it even harder for at least existing analysis systems. And also, you have to keep in mind, I didn't mention this really before, the WebAssembly is just harder to read, right? So it's like a binary format, so there's more reverse engineering involved, and it's just so low level compared to the JavaScript. So it will also mean that there's more involved for manual analysts compared to maybe a JavaScript exploit. And then one thing I came up with, it's just an idea. Who knows if it ever happens, if you have some genius, malicious person out there. But as I showed you in the beginning, these things can call into each other, right? So we have JavaScript that can call WebAssembly functions and the other way around. So what we could do, and I call this intertwined code, is that you basically call from one into the other all the time, and really, so imagine an attack that's not really, it's neither a JavaScript exploit nor a WebAssembly exploit, but it's actually only parts ever exist of one or the other, and they constantly call into each other. So that will be, if you're writing analysis system or some defense mechanism would make it really hard for you because, you have to analyze JavaScript and WebAssembly at the same time and then track all these calls into each other, right? Okay. Just some ideas what we could have. Yeah, that basically brings me already to my conclusion, which is good. So we've seen an exciting new feature for the web platform, but also for attackers. And currently the sites usually use it for crypto mining, sadly. It enables some novel obfuscation techniques because you're now running low-level code. Yeah, if you ever create a defensive system, then remember WebAssembly is out there. So keep that in mind. Okay. And, we have time for questions now. Or if we don't, or if I'm not able to answer them now, you can also contact me.